Welcome to the deep dive. AI models usually learn from video by looking at tons of individual shuffled clips. Well, today we're diving into something pretty different, training them on continuous, unbroken video streams. It's much more like how we experience the world.
Exactly. And that's the key point. The standard way, assumes every piece of data is independent and identically distributed, or IID,
Right, the IID assumption.
which works fine for shuffled data.
Right.
But when you're feeding a model a constant flow of video, the frames right next to each other are super similar. They're highly correlated.
Makes sense. A street view doesn't change dramatically from one frame to the next millisecond.
Precisely. And this similarity, this high correlation, it actually messes with the standard learning process. Performance can drop quite a bit. We'll see some examples.
It really throws a wrench in the works. So that's where this new research comes in. They're proposing something called orthogonal gradients. Okay, let's try and unpack this a bit. Imagine the model watching the video, trying to figure out how to adjust itself, how to learn. What do these orthogonal gradients actually do?
It's helpful to think about it geometrically. So when consecutive video frames are very alike, the updates or adjustments the model wants to make based on those frames are also very similar. They tend to point in almost the same direction in this high-dimensional learning space.
Ah, okay, so it's like trying to learn by taking tiny steps in basically the same direction over and over.
Exactly. You're not really exploring new learning directions efficiently. Orthogonal gradients essentially force each new adjustment, each gradient update to be perpendicular or orthogonal to the previous one.
Perpendicular, so totally independent directions.
Right. It makes sure the model is learning something new with each step, rather than just reinforcing what it learned from the very similar previous frame. Think of it like learning a sequence. You don't just repeat the exact same tiny muscle twitch. You learn the next distinct movement.
Okay, that helps visualize it. It's about forcing the model to capture the new information in each moment, not just dwell on the redundancy. So the researchers, they put this orthogonal idea to the test. First up, learning from just one single long video.
Yeah, this was pretty interesting. They used a model called Dora and trained it on one continuous video, almost 2 hours long, of a walking tour in Venice. Just one long stream.
Now, intuitively, you might think just showing it the video sequentially would work fine, right?
Well, not so much with the standard optimizers like AdamW. Yeah. When Dora was trained sequentially on this Venice video using standard AdamW, its ability to perform on a downstream task, like classifying images from ImageNet, really suffered.
How badly?
Significantly. Compared to training on shuffled clips from the same video, or using standard pre-training methods, the accuracy using linear probe and KNN evaluation dropped quite a lot. You can see the numbers in their Table 1.
Wow. So the sequential nature really hurt it, but then they tried their orthogonal approach.
Yes, and when they swapped in their orthogonal AdamW optimizer for the sequential training, it was a completely different story.
A game changer.
Pretty much. The performance on the ImageNet evaluation jumped way up. It dramatically improved, even surpassing results where the model started just from random initialization. That's a huge difference, showing it really tackled that sequential correlation problem.
That's impressive. And they had visuals for this too, right? Showing the gradients.
Yeah, they included a figure 3, showing that during sequential training, the standard AdamW gradients were highly correlated, as expected. But with orthogonal AdamW, that correlation between consecutive gradients dropped significantly, looking much more like the behavior you see when training on IID, shuffled data.
Okay, so it works on a single long video. What about multiple videos streaming in?
Right, they scaled it up. They trained a different model, Video MAE, on large video data sets, something V2, and Kinetics 400. But again, training sequentially, simulating continuous streams.
How did they simulate the streams?
They used two main batching strategies. One was batch along time, where a batch consisted of consecutive clips from the same video. The other was batch along video, where a batch had clips from different videos, but all at the same relative timestamp.
Okay. Any difference between those strategies?
Yeah, the batch along video method, where you see the same moment across different videos, turned out to be generally more challenging.
Why is that?
Probably because those moments, even in different videos, might share similar visual features or actions happening concurrently, leading to higher temporal correlation between batches compared to just consecutive clips within one video.
Ah, interesting. So did the orthogonal gradients help here too?
They did. Across both batching strategies on the something-something V2 dataset, using orthogonal Atom W consistently improved the model's performance, measured by linear probe and attention probe accuracy compared to standard Atom W in the sequential setting.
And that's shown in their table too, I assume.
Exactly. What's also quite interesting is they saw some improvement, though smaller, even when using orthogonal Atom W with the traditionally shuffled clips.
Really? Even with shuffled data?
Yeah, it suggests that maybe even in shuffled data, there can be some subtle interbatch correlations that the orthogonal approach helps mitigate. They saw similar positive trends when pre-training on the Kinetics 400 dataset and then evaluating on something-something V2 as well.
Okay, so single video, multiple streams. What else? Future prediction.
Right, the third scenario. They trained a model specifically to predict future frames in continuous video streams. This is also a form of test time adaptation where the model keeps learning as it sees new data.
Like a robot needing to anticipate what happens next in its environment.
Precisely. They use datasets like Ego 4D, which has first-person video, and ScanNet with indoor scenes. The setup followed a prior framework called baby learning.
And the results. Did orthogonal Atom W make a difference?
It did. Compared to standard Atom W and also RMS prop, which was used in that original baby learning work, orthogonal Atom W achieved better results in predicting future frames. They measured this using pixel mean squared error, MSE, and peak signal-to-noise ratio, PSNR.
Better predictions both within the stream it was learning from and even generalizing a bit outside of it.
Yes. Table 3 shows improvements for both in-stream and out-of-stream performance on both datasets. It really highlights the potential for this method in scenarios requiring continuous adaptation.
So pulling it all together, what's the big takeaway here?
Well, the core idea is that these orthogonal gradients offer a really neat geometric solution to a fundamental problem, learning effectively from continuous, highly correlated data streams like video.
It directly tackles that issue of the model getting stuck, making redundant updates because the input isn't changing much frame to frame.
Exactly. And the implications could be quite significant. This might be crucial for developing AI agents that can learn continuously on the fly from their real-world sensory input cameras, microphones, you name it.
Which could also have benefits for privacy, right? If the model can learn from the stream directly.
Potentially, yes. It might reduce the need to store, shuffle, and process these massive video datasets offline, which always carries privacy risks.
It's interesting, though, they did note a slight underperformance when they tested orthogonal Atom W on standard image classification, like ImageNet classification from scratch, where the data is already IID.
Right, that's in their appendix, Table 10.
Yeah.
It suggests the real strength of this method isn't necessarily as a general-purpose optimizer replacement, but specifically for handling that temporal correlation found in sequential data like video streams.
So it's a specialized tool, but a potentially very powerful one for this growing area of continuous learning. So, final thought. Where does this point us?
For me, this whole move towards learning from continuous streams feels like a significant step closer to how biological systems like us learn. We don't get shuffled clips of life.
Yeah.
We experience a continuous flow. It makes you wonder, what other principles from biology, what other learning mechanisms inspired by how we learn might be out there waiting to unlock the next big advances in AI.
Absolutely. It's fascinating stuff. Definitely food for thought. Thanks for taking that deep dive with us today.
My pleasure.
Until next time.